So I'm going to talk to you a little bit about pressure volume physiology. I think you've already seen an example of what pressure volume physiology looks like. And so what I'm going to really first talk about today are integrative cardiac physiology and PV loops, some key PV analysis parameters, things that you might want either in your basic science or drug discovery environment to tell you something about either pathophysiology. I think I heard something about congestive heart failure and heart failure models, cardiac function. Certainly we'd like to give you some takeaways on that today. And then obviously the PV loop applications as well and how those can be applied to your different disease settings. So as you saw today in the lab, hopefully, we were able to generate pressure volume loops that look very much like the one you see here. And as with any graph, it's always important to let the graph speak to you. And the way to let that happen is by first understanding the axes. Okay, so on the x-axis, and this will always be the case, we will see volume, right? On the y-axis, we will see pressure. And if the catheter is in the left ventricle, this is a pressure volume loop. Okay, and the reason, does anybody know why the volume is on the X and not the other way around? Any thoughts around that? Okay, so when one is graphing data, the x-axis is always the independent variable, right? The one that we can manipulate ourselves. All right. The y-axis is the dependent variable, that which changes in response to how we manipulate the x. Right. So back when we were all in middle school algebra, we saw f of x. F of x actually is y, and what that means is y is a function of x. So when we manipulate volume, we will see a change in pressure. Okay. So just to start you out, walking around the curve, around the loop, at the point here labeled 1, this is where the mitral valve opens. Okay, and the mitral valve actually is the valve between the left atria and the left ventricle and allows the ventricle to fill with blood. And so certainly what we can see is that there's a change in volume status here. After the mitral valve opens, we have diastolic filling, shown by number 2. Okay, and what you'll also notice is that there's really, although volume is changing, notice no change in Y, right? So this means that as the heart is filling with blood, there's not a real change in pressure under normal conditions. Certainly that changes in the setting of disease, and we can point that out a little bit later. Number 3 is when the mitral valve actually closes, and you can tell this because there's no longer an increase in volume, right? So the only way blood can fill the ventricle is if the valve is open, right? So at this point, the mitral valve is closed, but also the aortic valve is closed. All 4 valves in the heart are closed at this point. During this period, we see isovolumetric contraction. So if we break this word down, iso means same, volume, right, meaning there's no change in volume, same volume. And actually no real change in length. So there's isovolumetric contraction. So the heart is actually starting to generate pressure. Notice, while there's no change in volume, this is a straight line up, we have a dramatic increase in left ventricular pressure. At this point, the pressure in the heart exceeds the pressure in the aorta, and the aortic valve opens. Remember how I said earlier, in nature, everything flows down its pressure gradient. Everything flows down its concentration gradient. The only way that blood can be ejected from the heart is if the pressure in the left ventricle exceeds the pressure in the aorta and the aortic valve opens. So the aortic valve opens, and what do we see? Well, there's actually now starting to be a reduction in volume, right? We're going this way. So these loops always move counterclockwise, right, in this direction. So we have a reduction in volume that's occurring here, but what do we notice? Pressure continues to rise during this period. So the heart is continuing, and that is because the heart is continuing to wrap as the way the cardiac muscles are shaped around the ventricle. It's like wringing out of a dish rag, if you will. So the heart actually wrings itself out to be able to fully eject blood. And what we see here is that while volume is being reduced, pressure is actually increasing. until the heart is no longer being able to eject much more blood, and then the pressure starts to fall. Once the pressure reaches this point, right, number 7, the pressure in the aorta actually exceeds the pressure in the ventricle, and the valve closes. Competent valves, as with most systems, only function in one direction, right? So if they're, again, under normal conditions where there's not aortic regurgitation or any aortic valvular damage, the valve snaps shut when the pressure in the aorta exceeds the pressure in the ventricle. At this point, we have, again, a limb of the curve that is perpendicular to the x-axis, where we see a great change in pressure with no change in volume, right? So this is isovolumetric, same volume relaxation. This is the heart actually relaxing until the pressure in the ventricle falls below the pressure in the mitral valve or in the left atria, and the mitral valve opens again, and then the cycle starts all over again. So that is one complete cardiac cycle. Make sense, everybody? So this pressure volume loop can actually be superimposed against something called the Wigger's diagram. So this diagram actually came from a famous physiologist around the turn of the last century, around 1905 actually, where the relationship between pressure and volume and flow were all characterized in excruciating detail. And I leave this to you to go through on your own, and we can certainly talk about this in the laboratory. But basically what you can see here is that these are the relationships between time and volume, shown in the lower panel, and pressure in the left ventricle, shown in the upper panel. And what we can see here is that, as we showed you in the pressure volume loop, during diastole, the pressure is very, very low, almost zero. Then we have isovolumic contraction, a large increase in pressure, exemplified here by no change in volume. Then we have the aortic valve opens. This is the pressure in the ventricle exceeding the pressure in the aorta. We see now volume falls very, very quickly, right? So about two-thirds of ejection occurs during the first third of systole. And then we have the pressure in the ventricle starting to fall. Once the pressure in the ventricle falls below the aortic pressure, the aortic valve closes. No more change in volume. We have isovolumic relaxation, and that's occurring here. And then when the pressure in the ventricle falls below that in the mitral valve or in the blood incoming to the left ventricle, the mitral valve then again opens. Right? So if one were to take these pressures and these volumes and superimpose them on an XY coordinates, you would get a pressure volume loop. Make sense? Indeed, there it is. And you can tell Jeff is very well prepared here. So again, our same phases that we see here in the pressure volume loop. Now there's a couple of other interesting features shown on this figure. Most notably, there's a slope line here that's called the ESPVR, or end systolic pressure volume relationship. And there's an EDPVR, end diastolic pressure volume relationship. This allows us to, when certain manipulations are made to the heart, this allows us to diagnose whether there are systolic or diastolic dysfunction with the heart. And that needs to be done by altering loading conditions of the heart. Small animals, rodents in particular, are very sensitive to changes in loading conditions, so it's an ideal model for being able to evaluate the end systolic and end diastolic pressure volume relationship. In the setting of systolic impairment, myocardial infarction, for example, there will be a change in the end systolic pressure volume relationship. In the setting of diastolic dysfunction, cardiac fibrosis, long-standing arterial hypertension, cardiac remodeling, calcium dysregulation, there will be a change in end diastolic pressure volume relationships, and this speaks to the ability of the heart to relax and accept incoming blood. So talking about integrated cardiovascular function, certainly the heart is a very unique and very highly specialized demand pump, meaning that it can respond to changes in preload. it can respond to changes in afterload, and certainly can be demanded to increase its cardiac contractility. All of us have experienced the sensation of climbing a flight of stairs and feeling our heart beat a little harder, a little bit faster. That's because we're putting a demand on the system to deliver more cardiac output. So the heart responds to the demands of the metabolism by increasing cardiac output, and that can occur through any number of ways: by loading the heart with increased venous return or preload, increasing the cardiac performance of the heart, contractility, and actually in terms of responding to elevations in systolic blood pressure. For example, when somebody lifts weights, they actually are contracting a lot of their skeletal muscle, which causes an increase in systolic pressure and an increase in afterload. And the heart can certainly respond to any of those demands under normal conditions. We achieve that certainly by when we change preload, which you'll see in the laboratory today, the amount of blood. So preload is the amount of blood coming into the heart, the amount of stretch that the heart experiences. That can be changed by changing stroke volume. Heart rate can also be changed. Certainly we have all experienced, and I know for the graduate student in the room, public speaking and giving your seminars, right, certainly can make your heart beat a little bit faster. At least makes mine beat faster. And heart rate will also influence cardiac output, right? So cardiac output is the relationship or the product of stroke volume times heart rate. The amount of blood being pumped out on a per beat basis times the number of beats per minute will give us the amount of flow being generated by the heart. And interestingly, when we summate stroke volume and heart rate to get cardiac output, and we give us the product of cardiac output and total peripheral resistance, we can actually get arterial pressure. Now, this is a very important relationship to be able to understand, because it's going to tell you something about cardiac performance and how the heart will respond to those demands on the system. And one way of thinking about this is the electrical circuit analog of Ohm's law. Right? Ohm's law says V equals IR, where V is voltage, I is current, R is resistance. The hemodynamic analog of that is arterial pressure. Pressure is like voltage, right? It's a potential, it's pushing. Cardiac output is liters per minute or mils per minute in a rat or a mouse. That is flow, and resistance is R. So V equals I times R. And then one can certainly rearrange that equation in any number of ways to be able to better understand peripheral resistance and cardiac output in the setting of high or low blood pressure. So again, going into a little more detail around what these terms mean. Preload is the degree of cardiac muscle stretch at the onset of myocardial contraction. So if you recall, I told you the heart is a demand pump. So the heart can be, in a very simple way, conceptualized like a rubber band. The more you stretch, the more it will snap back. So the more you fill the heart under normal conditions, the more it will snap back, the more you load the heart. In the setting of heart failure, and especially decompensated heart failure, the heart becomes overstretched and loses its ability to snap back, and that is what's called decompensation. But the heart's ability to compensate is when it's working under normal conditions, that the more we stretch it, the more it will put out. Okay? And again, this is often expressed as the end diastolic volume or pressure. So it's the amount of load on the heart prior to contractions, preload. We're going to demonstrate the Frank-Starling law of the heart to you today in the lab in real time, but what I did want to point out is this is an example of how I was referring to the heart as a demand pump and functioning somewhat like a rubber band. This shows the relationship between volume, end diastolic volume, and output or contraction of the heart. And what you see, again, if we think in terms of x and y, with x being the independent variable and y being the dependent variable, the more we manipulate volume, the more we see an increase in pressure during systole. And you can see this is actually a very steep relationship under normal conditions. Okay, so as we add small amounts of volume to the heart under normal conditions, we get large changes in output. Interestingly, though, under normal conditions, during diastole, changes in volume don't really influence the heart within its normal working range, right? Because the heart, when it's relaxed, is actually quite distensible under normal conditions. However, once we get to a certain point, about 200 mils or 200 mils in a large mammal, as we get beyond that point, we start to see dramatic increases in diastolic pressure with no real addition in cardiac output or systolic performance. Does anybody know why that might be? Any thoughts around that? It all has to do with sarcomere length. So if we all are familiar with the sliding filament theory of how cross bridges work, if you actually stretch the heart too far that the cross bridges no longer overlap, right? At that point we are now stretching the heart and adding a lot of pressure during diastole, but since we don't have any cross bridges to form, we can't generate any more pressure. Okay, so that is really the theory behind decompensated heart failure, that when we stretch too far, the heart can no longer contract well. That's heart failure.
You start leaking blood too, don't you?
Start leaking blood. Well, what can happen under those conditions is that there can be edema formation as a function of elevations in pressure, but it's a little more complicated than that because as diastolic pressure increases in the ventricle, most blood flow in the myocardium occurs during diastole, and so if the diastolic pressure is very high, and you have to remember that we're talking about capillaries, the flow is actually somewhat reduced. So it's a little more complex than that, and I don't want to get into that level of granularity right now. But basically, the bottom line here is, and this is really the Frank Starling law of the heart is captured here in our bracketed term here, which is the heart will pump what it receives under normal conditions. It's a demand pump. The more you stretch the heart, the more it snaps back. Again, speaking about afterload, a little more detail. Afterload is the force against which the heart contracts during systole, and this is often expressed as millimeters of mercury. Now, lots of people, experts in the field, experts in cardiac physiology, have a lot of discussion around what afterload really is. The easiest way to conceptualize it is the pressure that the ventricle has to generate to force the aortic valve to open, which is in millimeters of mercury. If one was interested in an aortic coarctation model, right, or an aortic banding, aortic coarctation, where there's a band put around the aorta, the heart has to generate much more pressure to overcome that resistance, right? Because that band, or the constriction, creates a resistor that the heart has to generate pressure against to force the aortic valve to open. So that's an increase in afterload. Contractility, again, this is a term that is often debated among experts in cardiac physiology, but essentially it is the intrinsic ability of the cardiac muscle to contract once it's been activated, and is a measure of cardiac pump function. So contractility most notably responds to changes in catecholamines or sympathetic drive, right? So the fight or flight response is often referred to as sympathetic drive. So when we are, prehistorically speaking, right, if our ancestors were being pursued by prey animal, right, and we had to fight or flee, the ability to increase cardiac output and increase contractility to deliver blood to our exercising skeletal muscle to enable us to survive that threat, fight or flee, was very beneficial. So this is an adaptive mechanism that mostly responds to sympathetic drive, the fight or flight response, generally speaking. So the key analysis parameters, things that we're going to be looking at today. There are a variety here. Stroke volume, again, the amount of blood that is being pumped by the heart on a beat-by-beat basis. Cardiac output, the amount of blood in liters or mils per minute that's being pumped out, again, is a product of heart rate and stroke volume. Stroke work tells us something about the area within that's bounded by the pressure volume loop. It tells us it's a function of work of the heart. And so folks who do muscle work here, right, it's a relationship between length and tension that's generated. And that is actually bounded by the curve and some other parameters that can be shown on the PV analysis. Ejection fraction, this is a very critical feature that we should be looking at today. Ejection fraction is one of the hallmarks of cardiac performance and actually is used clinically as a diagnostic for when a patient actually has heart failure. Clinically, you and I, and in our normal animals today, you'll see that ejection fraction is, the textbook number is about 2/3, about 66% or so. In rodents, it's a little bit higher, actually, about 70 to 75%. But ejection fraction in a heart failure setting is defined clinically by a reduction in ejection fraction, depending on the clinician you speak to, below 30 or 35%. That means you're only ejecting about half of the normal blood that would be ejected on a beat-by-beat basis. And this is clearly consistent with a failing pump, right? Not able to generate the amount of pressure and output as would normally be expected. DPDT, you saw that on our tracing in the laboratory, where DPDT is the derivative, the first derivative of the maximal change in pressure over change in time. It tells you something about contractility and how rapidly the heart can generate pressure, and also how rapidly the heart can relax during isovolemic relaxation. So we have both indices of systolic performance and diastolic performance. Tau is another, it's a very nice index of diastolic function. For those of you who have ever studied neuroscience, you know what the mono-exponential decay of an action potential looks like. And certainly tau is a reflection of that, and it is about, in very loose terms, it is the time it takes for 1/2 of a decay of the pressure. So it's about 70% of decay in pressure is about 1 tau, roughly. And what you can see is in diastolic dysfunction, the tau becomes longer. And we're talking about a very small amount of time. In a rat, the normal tau is about 6 to 7 milliseconds. Right? It's very small, 6 to 7 thousandths of a second. In the setting of heart failure or diastolic dysfunction, that can increase to 10 to 12 milliseconds, about double. So it doesn't seem like a lot, it's only an increase in 6 milliseconds, but when one considers that a rat's heart beats at 360 beats per minute, times 6 milliseconds per cardiac cycle, you're talking about an extra second or two per minute of extra relaxation time. Clearly not normal, right, in a rodent. ESPVR, the end systolic pressure-volume relationship, is exemplified by this line, shown here, where all of the end systolic points are connected together. And actually, this is a Starling curve. This is the Starling curve, if you recall. Starling's law is the more you fill the heart, the more it puts out. Here we have a normal pressure volume loop, and we reduce preload, and we can see how the heart looks as a function of changes in volume, filling, with respect to systolic performance. That is the end systolic pressure volume relationship. The end diastolic pressure volume relationship actually looks at the relationship between cardiac filling and diastolic pressure. And so necessarily, if you recall, as we fill the heart under normal conditions, there's very, very little change in pressure, right? So this is a very flat line. The end systolic pressure volume relationship is a very steep line. And these can change dramatically in the setting of systolic and diastolic heart failure. Preload recruitable stroke work is a little more of a boutique kind of endpoint, but can be something that tells you something about the ability of the heart to generate work as a function of filling. Certainly we will look at that today, and I'm not going to go into PVA. It's the pressure volume area. It's another index of work. So again, stroke volume is the amount of blood being pumped out of the heart on a beat-by-beat basis, and can be derived by looking at the relationship between the end diastolic volume and the end systolic volume. So if you recall, in our pressure volume loop, we had an end, and here is a exemplified pressure volume loop, looks like a square. This is the end diastolic volume when the heart is filled. This is the end systolic volume when the heart is now empty. The difference between this volume and this volume is stroke volume. And importantly, and we're probably going to see this in the next slide, actually, is this difference allows you to calculate ejection fraction, right? So if we have an end systolic volume of 100 and end diastolic volume of 100 and an end systolic volume of 50, the difference here is 100. So if we take the difference and we divide it by the amount that we were filled with, 100 divided by 150, that equals 2/3. A textbook normal ejection fraction of 66%. And again, in a clinical setting or in a disease setting, failing hearts, systolic volume, stroke volume is highly sensitive to afterload changes, and we'll see that in some of our examples as we go forward. So again, stroke volume can be influenced by preload. So if we were to increase the load in the heart, let's say that we put a catheter in the animal's vein, and we give it a bolus of volume of either blood or saline, and we increase the load to the heart, we are going to increase the stretch of the heart, and you can see we are going to, in turn, increase the end diastolic volume, and then what happens to our output? Well, the heart's going to generate more pressure and come up with a greater amount of ejection here. So we're actually demanding the pump increase output, and we see a change in stroke volume. If we have an increase in afterload, recall the aortic stenosis or aortic coarctation method. The heart has to generate a much greater pressure at the same volume to be able to overcome the pressure in the aorta, and as a result, afterload falls. And we might be able to do that today manually by isolating the aorta and actually constricting it and showing you an increase in afterload and how the heart responds with respect to a PD loop. Any questions? We're going kind of fast here. Okay, ejection fraction, I touched on this briefly. Again, it is the fraction of end diastolic volume that's ejected. And so it is the stroke volume divided by end diastolic volume, and it is always expressed as a percentage. It's used as an index of clinical cardiac contractility. Again, normal being about 66% or above 60%. Heart failure, severe heart failure. This is a person who will actually need, if they're below 20%, they'll need Lasix. They won't be able to, they'll have to be diuresed because they won't be able to generate enough output to maintain blood pressure normal to be able to actually force fluid through their kidneys, and they'll start to take on water, actually. But clinical heart failure is diagnosed as a reduction of ejection fraction below 30 or 35%. This is severe heart failure, as it says here. DPDT max and min, again, is the rate of ventricular contraction and relaxation. An increase in contractility will give you an increase in DPDT max. And what should be pointed out here is that there's both a positive DPDT max and a negative DPDT max. Positive DPDT max is the rate of pressure generation during systole. Negative DPDT is the rate of pressure reduction or relaxation, right? And the maximals of those tell you something about contractility and about relaxation. Tau, again, is another index of diastolic performance, and if it's deranged to too great of a degree, it's diastolic dysfunction. And the beauty of tau, as pointed out here, is that it's relatively load independent. It tells you much more about the calcium handling within the heart, the viscoelastic properties of the myocardium, and is somewhat load independent. So it can tell you something about the heart itself, independent of hemodynamics. The isovolumic relaxation constant is really how tau is defined, and I think I told you a little bit about that. I'll go to the board later in the day and show you a drawing or make you a diagram about what that means. But basically, it refers to the time constant of decay of the pressure rate. Again, can be used in the evaluation of heart failure, and again, represents the exponential decay, which is why it's referred to as actually negative E, tau, decay of ventricular pressure during isovolumic relaxation. And we'll show you that a little bit later. Again, ESPVR, the end systolic pressure volume relationship, is the maximum pressure generated by the LV at a given volume. And so you can see under normal conditions, we have a very steep end systolic pressure volume relationship. When we have cardiac dysfunction, we actually have a reduction in the slope of the ESPVR here. Again, it's an afterload-dependent index of myocardial contractility, and a decrease in the slope is directly related to a decrease in contractility here. The slope of this line is a measure of elastance, and it is load-independent, so it's a better index, for example, than ejection fraction, cardiac output, or stroke volume. And I often use this analogy to explain why ESPVR and EDPVR can be used to evaluate cardiac function. What you saw in the lab earlier today was a steady state pressure volume loop. Right? The heart, the animal had normal blood pressure, it was under a normal respiratory rate, it was breathing normally, blood pressure was normal, loading of the heart was normal. And so the PV loop, for the most part, without the effects of a few respiratory oscillations, didn't move much. The analogy I'd like to use is the brakes in your car. One doesn't often know that the brakes in their car don't work until they're speeding down the highway and they need to hit them, right? So if you're cruising at a constant speed of 65 miles an hour on the freeway, and suddenly you have to slam on the brakes, you have to load your car, load your brakes, then you find out how well they work. If your brakes have integrity, the car stops very rapidly and can respond. Same thing applies to the heart. Under normal conditions, under steady state conditions where it's beating at a constant rate, constant load, the heart responds quite well, even in settings of failure sometimes. But when one changes the loading conditions of the heart, either preload or afterload, right, you're asking the heart to respond to a change. And then you find out how well the heart works, right? So we use ESPVR and EDPVR to actually evaluate the ability of the heart to respond to a demand, right? And to take that to a more real life situation, the primary clinical complaint of somebody suffering from heart failure is, I get exhausted when I climb a flight of stairs. Right? I can't climb a flight of stairs. Why? Because the heart cannot respond to that demand. Right? So we do this experimentally in the laboratory by changing loading or demand on the heart, and we see how the heart responds to those demands. EDPVR, again, is a function of the passive filling curve of the left ventricle. Under normal conditions, it's very, very flat. And as we have some diastolic dysfunction, the slope of that line changes. So what this means is that under normal conditions, as you add volume to the heart, no real change in pressure. Right? It's very compliant, very distensible, very elastic. In the setting of diastolic dysfunction, though, the heart becomes stiff and non-compliant. You can have cardiac fibrosis, you can have cardiac hypertrophy, thickening of the wall. And as you try to fill the heart with blood, there is a fairly dramatic increase, relatively speaking, in end-diastolic pressure. This is an upward shift in the end-diastolic pressure-volume relationship. And you can see that a decreased compliance can be related to ventricular hypertrophy. A decrease in compliance under these conditions is an upward shift in the line. Decreased compliance, actually, if we go from the black line under normal conditions to the blue line, can be related to dilated cardiac myopathy, where the heart becomes very dilated, very distensible, and almost flabby-like, and cannot generate pressure. Preload recruitable stroke work, again, is the relationship between stroke work and end-diastolic volume, and you can see that essentially this tells us something about the ability of the heart to do work. And here we have the relationship between end-diastolic volume and stroke work, which can be defined by the area of the pressure-volume relationship. And as we change end-diastolic volume, we see a very nice linear relationship here under control conditions. When we have heart failure, the ability of the heart to generate work as a function of volume goes down, right? So what this means is that at any given volume, the amount of work generated by the heart is less. So you need to have a greater amount of volume to be able to generate the same amount of work. And that refers to the heart dilating and no longer being able to generate force. The pressure volume area, again, this is more of a real cardiac mechanics kind of endpoint, but it does represent the total mechanical energy generated by the heart during ventricular contraction, where there's both potential energy and stroke work. So stroke work is the area actually bounded by the pressure volume loop. And if we extend these axes extend these lines from the ESPVR and EDPVR back to the intercept, we actually see the amount of potential energy. Right? So the heart actually stores potential energy as we fill it, right? So it stretches and then it contracts. There's both an active component and a passive mechanical elasticity component that can be captured in the potential energy area here. And so if you want to really look at the amount of pressure volume area, you can look at this. And certainly the Millar system and the 80 chart system can give you this data. PV loop applications. I think I've talked about this a lot already, but just to kind of drive this home, we can look at diastolic dysfunction in any number of ways. And so certainly there are multiple indices here that we use in our drug discovery efforts to evaluate how a compound influences cardiac mechanics. Notably, the left ventricular end diastolic pressure. That's the pressure at end diastole. So that can be a function of cardiac stiffness or increases in cardiac in filling volume, right? So as we fill volume, we will move to the right, and this will go up. Or if we have left ventricular stiffness, at any given volume, we'll have an elevation in LVEDP. So those can be a couple of different harbingers of cardiac dysfunction. The minimal or negative DPDT tells us something about rate of relaxation, rate of pressure decay. End diastolic pressure-volume relationship tells us about the relationship between volume and pressure. And tau, again, is the monoexponential relaxation coefficient, a load-independent measure of cardiac relaxation. And again, this is a very well-known figure now. This is actually a great review for anybody who's doing this kind of work. The first author's name is Origema. It was from Circ Research in about 2006. This is a very classic review now showing how pressure-volume loop analysis can be used to study a variety of different cardiac dysfunction states. And so here we see our normal pressure-volume loop with a normal ESPVR and EDPVR. In the setting of systolic heart failure, post-MI, we see a change, a reduction in the slope of the systolic and systolic pressure-volume relationship, and a rightward shift in the PV loop relative to normal as the heart starts to dilate and accept more blood. In diastolic heart failure, we actually see somewhat of a leftward shift in the PV loop, a normal and systolic pressure-volume relationship, still very steep, but we can see that there's a leftward shift in the EDPVR, so that as the heart becomes stiff and cannot accept blood well, at any given volume, there's an elevation in pressure. And these, again, seem slight, but if one remembers that the heart is being filled by a venous system, a small change in pressure here makes it harder for the venous system to be able to overcome that and fill the heart. Truly a very good paper and worth a read, I think.